Good day, I'm Dr. T and welcome to my office. So today we are jumping into the wonderful world of physics. In particular, we're jumping into Newtonian physics with the study of motion in this video. But as I like to start out each one of these sections, I want to do a bit about further reading. If you want to dive a bit deeper, OpenStax has a physics textbook. I always like OpenStax. They do a decent job and they're free. LibreText has a whole swarm of physics textbooks. They do a good job. So, hey, always nice to check those folks out. And Complexly, they've got Crash Course Physics, a great introduction to the field. So if you're wanting to dive a bit deeper, there's a few options. Don't feel obligated, like always. So let's dive into motion. But to do so, we need to take a little bit of a detour through math. We're actually going to take two detours through math, but the first one needs to be the first thing we cover, and that is the wonderful world of vectors. So let's provide some context. Remember several videos ago, I talked about units. I spent a whole video talking about units and measurements and that kind of stuff, but I didn't bring up one rather important concept. And that is we can divide units into two parts based on an interesting property. So units are all going to have a magnitude, basically how much mass, how fast, that kind of stuff. And for units where they have a magnitude, but that's about it, we call those scalar units. However, there is another set of units that have a magnitude and a direction. If you're a fan of Despicable Me, you know the answer. Those guys are vector units. So vectors are effectively a number with a direction. By the way, you may be aware that there's a bit of drama in the math space revolving around the type of symbol used for multiplication. Vectors are partially why there's this drama. I know enough about the drama to know it's there and to stay away. So just giving you a heads up. When it comes to mathematical symbols for multiplication, there's a lot of drama, and some of it is due to vectors. So we want to dive in and talk a little bit about vectors because when we're dealing with motion, we're going to be dealing with, well, direction. And so to understand direction, we need to understand vectors. It's entirely obvious. You already got it. You just may or may not know what you already know. Okay, so we can represent a vector pretty straightforward as an arrow. It's pointing in the direction it's going, and its length is relative to its magnitude. And with this, let's say we've got two arrows. If I've got two arrows and they're pointing in the same direction, then I can add them together to get a longer arrow pointing in the same direction. And that would be the net vector or the added vector. We're not going to deal with multiplication here, thankfully. Okay, now let's say I've got two vectors, but they're pointing in opposite directions. So in this case, we're going to subtract them. And as such, we are now going to get our new combined vector, and it's going to be shorter. And potentially it could be pointing in the opposite direction, depending on which one is of which length. Now, what if they are not pointing in the same direction or opposite, but they're pointing in different directions? Well, congratulations, you have yourself a triangle. So we can rearrange them to form two sides of the triangle, and then the net vector, the one where we factor them both in together, that will be the hypotenuse of our triangle. And as such, hey, we got ourselves a nice looking triangle over here. Okay, so we've got the concepts of vectors. And yeah, that does mean you actually might be using something like Pythagorean theorem with vectors. So much fun, you know, a squared plus b squared equals c squared. You know, you remember that one, I assume. Which also means that if you're ever teaching math and a student goes, when will I ever use this? Well, adding up vectors. Okay, they probably won't like that answer, but you get the idea. Actually, trigonometry, there's tons of uses for trig. But let's move into some physics, and we're going to look at the relationship between position and time. So we're going to be doing motion, and so of course motion, something is moving. It is changing its location over time. And so I'm going to pop up a graph, and this is going to be a one-dimensional. So this would occur in 3 dimensions, so we'd have 3 different graphs. We're just going to look at one because this is more than enough to deal with. Okay, so in this case, I've plotted the location of my thing over time. I'm not putting units on this thing. We can sort that out later. But in this case, it's moving pretty much just kind of going at a constant rate. It's got a nice constant speed. It's traveling over time. Yay. If I wanted to figure out how fast it was going, what I would do is I would find the slope of that line. I would take the change in distance and divide that by the change in time. You'll notice I'm using little triangles in front of those. The little triangle is the Greek letter delta. It literally just means final minus initial. Unless it's over a reaction arrow from the previous video, in which case that means add heat. But we're doing physics, not chemistry at this point, alas. So in this case, it will be final minus initial. Okay, so we've got our slope, and that is going to be our speed, but it's going in a specific direction. Speed is a scalar quantity. Remember, scalar quantities have a magnitude, but no direction. We're actually going to be dealing with velocity. Velocity is just like speed, except for it has a direction. It is a vector quantity. And in this case, we're going to say that our thing has a velocity. It's whatever the slope of this particular line is. Okay, let's update the graph. Now, it wasn't keeping this nice constant velocity. Notice how it was kind of slow to start with, and it sped up, and then it slowed down again. Well, in that case, I could just redraw the original line. It ended at the same spot at the same time. I could do the slope of that one, and that would be my average velocity, which is perfectly good. That may very well be what I want to know. But if I want to get a bit more resolution, well, what I'd have to do is the slope of each one of those line segments. Okay, we're going pretty good here. Let's update this again, though. Okay, so this is a curve. It's all curvy. There's no real lines here. I mean, there's one kind of in the middle, but okay, this is going to be a little bit more awkward. So I could still do the average. That would be pretty straightforward. But if I want to figure out the slope, the velocity, there's no line. So this is going to be a bit of an issue. But this is one that Sir Isaac Newton starts tackling. In order to explain his physics, which is the core of what we're covering today, and things that evolved from that, he developed a series of math called calculus. And I want to introduce a few ideas of calculus. Don't worry, we are not doing any calculus equations. The ideas of calculus are actually quite simple, something that even a small child could definitely understand. The equations and solving the mathematics, that's a different story. To be honest, it's been a while. I'm very rusty. We're not doing that. But the idea here is if I look at my chart, I could imagine having some line segments kind of averaging out parts of that chart. And then I could shorten them up and have more of them. Basically, I'm slicing it apart. I'm going for a higher and higher resolution, more pixels, and I'm drawing the lines between the pixels, and more and more and more pixels. So I'm making many, many more line segments. They're very, very short, but I can still calculate their slope. Well, what Newton does with calculus is says, well, what happens if we added an infinite number of line segments and they had an infinitely small length to them? Okay. Well, doing some math called a derivative, you can calculate what the slope of each one of those tiny little line segments would be. You get an equation. You put an equation in, you perform the derivative, which is another type of equation, and you get an equation out. Okay. That gets described instead of delta position or delta x, x is the variable we use quite often for position, we would do lowercase d. So dx, and we're not going to do delta t because this is an infinitely tiny amount of time as well. So we'll do dt. Okay, so if you're familiar with Zeno's paradox, that's the one where if an archer fires an arrow at some point, it gets halfway to the target, then 3/4, then 7/8, and so on and so forth, and kind of like, but it always gets closer and closer. It never actually reaches the target, but of course it reaches the target. For those of you who are familiar with calculus, if you think about that in the terms I just described for the line segments, you're like, oh, wait, Zeno is discovering calculus a couple thousand years before Newton. So it's an interesting way to kind of frame other disciplines into it. Okay, so we can do what we call the first derivative. And so the first derivative is we perform the mathematical operation that predicts what the slope at every individual point would be, and we get ourselves a new graph. Okay, I just whipped these things up in Inkscape, not any like MathCAD or something, so bear with me. These graphs are probably hideous, and if you're really good at math, you're probably going like, no, that's not it. Once again, just whipped up in Inkscape. Now, that gives us our velocity. So this one would be describing our velocity at any point, because remember, the slope is our velocity, and well, we are describing the velocity at every instance in time. But you know what? We could notice a couple things from here. One, that's not a straight line. That's a curve. So what's the change in velocity? Velocity is a change in position over time. The change in velocity over time is what we call acceleration. So we could do the same things to it. If it was a straight line, we could find the slope, or in this case, we can do another derivative, what we call a second derivative. And so the second derivative of position is going to be acceleration, so dv over dt. And we've got ourselves some acceleration. And this leads us into some of our interesting topics that we're going to dive into, because we're actually going to focus quite a bit on acceleration. Because what Sir Isaac Newton figures out is that acceleration is related to two other terms that are going to be incredibly important for what we're talking about. That of force and mass. He comes up with the equation F equals ma. This is one of those foundational equations in science. When we talked about models, this is one of the big ones, is this equation. And so for this one, if I exert a force on an object, I'm going to accelerate it inversely proportional to its mass. So if it's really heavy and I push on it, it's not going to push much. Okay, so we've got F equals ma. Let's use an example of how we're going to apply this. So I've got myself a box over here. Newton gives three laws. The first two are basically the same idea. An object at rest stays at rest unless a force is acted on it. If you go back to F equals ma, if F is 0, a is 0. Likewise, an object in motion will stay in motion unless a force acts on it. Once again, if F is 0, a is 0. Keep in mind, acceleration is change in velocity. That could mean speeding up, that could mean slowing down, that could mean changing direction. Your car has three accelerators. The right button makes you go faster, the left button makes you go slower, and the center wheel makes you go back and forth. All of which are acceleration. Because remember, velocity is a vector quantity. Okay, so let's look at this particular box. Matter has a property called inertia, where it wants to resist change in velocity. Basically, this is the m in the F equals ma. So I know the mass of this particular box. The more matter, the more it's going to resist acceleration. Once again, this is the m in F equals ma. And with this one, I've got a bunch of forces acting on it. So I want to simplify these into a nice net force. Net force is when I take all the forces and I basically add them up, keeping in mind that these are all vectors, so some of them, when I add them together, are actually subtraction, and some of them will actually be a triangle. I conveniently made this one so it's not a triangle, so we don't have to deal with the triangle just yet. So if I look at this guy, I've got a 100 Newton force pushing to the right. Well, roughly speaking, if you were to pick up, say, a 10-kilogram dog or a little over 20-pound dog, that would be exerting, the gravitational force would be exerting 100 newtons down on your hands as you're picking up the dog. Okay, so I'm going to take this box. It's 5.1 kilograms, so we're talking, what, like 10, 12 pounds or so. And we're going to push that off to the right. But friction is a thing. Now, friction is somewhat unique in forces because it's always resisting force. So it's never going to accelerate you faster, not even in the other direction. It'll always try and accelerate you slower relative to the thing that you're on. Everything we're talking about, by the way, when it comes to velocity is always relative to the observer. So if you throw a ball, you're accelerating the ball, but if you're on the train, well, you're throwing the ball and the ball is going faster from the point of view of the tree next to the train than it is to you, assuming the train is in motion. But we're going to push this to the right with our force, but friction is going to push with 20 newtons back and is going to resist us. So we're going to have a force to the right of 100, a force to the left of 20. So we add those together. They're going in opposite directions. That means we subtract. We get 80 newtons. Oh, but wait, we have air resistance. This is based on the shape of the object. Friction is based also on shape. It's the surface area that's contacting the thing it's rubbing against, as well as the nature of the material. that are rubbing. Sandpaper is going to have more friction than ice, as well as the mass, how much force is being squished down and trying to get those things to merge. Air resistance is going to be heavily based on the shape. How easy is it to push the air away? How fast is it going? As well as the density of the air. Okay, we get 10 newtons of air resistance for this thing. And so that's going to subtract another 10 from our 100s, which became 80, and now is going to be 70. Okay, so I've got 100 newtons of force, but I'm canceling out 30. So the force pushing to the right is going to be 70 newtons of force. Let's look about up and down. Going down, we have the pull of gravity. That's 5.1 kilograms of gravity. Sorry, that's 5.1 kilograms. The acceleration of gravity is 9.8 meters per second. So we can plug that into F equals ma, and we can get a force of 50 newtons pushing down. Okay, so it's not clipping through the table, so the downwards force must be canceled by an upwards force. The upwards force from something sitting on something else, we call that the normal force. Particularly, it's actually not an upwards force, it's a force perpendicular to however it's sitting. So in this case, the table is flat, so the normal force is going up. But if the table is on a slant, then the normal force would be going diagonally. That will be important later when we do simple machines and inclined planes. Okay, now it's 50 newtons of force going down, 50 newtons of force going up. Those two are going to cancel, so we don't have any up and down motion. We're only going to the right. So my net force is 70 newtons to the right. I can plug that into F equals ma. I know the mass, I know the force. I can get the acceleration of 13.7 meters per second. Now, with that, I can calculate the change in velocity, because that's an acceleration. That's meters per second, which is velocity per second. So that means I'm changing velocity every second. Well, if I know how fast I was going to start with, which is not on this particular picture, and I know how long I exert the force for, once again, not actually on the picture, then I could take my time, multiply it by my acceleration. That would give me my change in velocity, or delta V. And then I could add that to whatever my initial velocity was, and boom, I have my new velocity. Which, of course, I could time it and see how long it was traveling, and that would tell me where it is. And it looks like my screens have gone to sleep. Okay, they're back. Now, we can actually use that whole path to our advantage. One of the best examples of using Newton's law is what we call inertial navigation. And this is the idea that you can use your acceleration. You can use an accelerometer, which is usually like a ball on a spring. Or you can do it with lasers if you want to do really fancy, but usually it's just a tiny ball and a tiny spring. Your phones are loaded with these things, by the way. That's how it knows which way's up. It's measuring gravity. Well, you can use this to calculate your acceleration. And remember how previously I had the position and then velocity and then acceleration graphs, and how we did the derivatives? Well, you can take integrals. Integrals are the opposite of a derivative. They undo a derivative. So I can take my acceleration, I can plot that over time, I can take the integral of that, I can integrate that, I can then calculate my velocity over time, and then I can integrate that and get my position over time. Inertial guidance is something that's used in quite a few areas. It was originally started for military applications, basically where is my missile going kind of thing. This is the meme or the copy pasta that you every now and then see. The missile knows where it is at all times. It knows this because it knows where it isn't. Basically, if you know where you started and you track the acceleration and you track velocity and you track your change in position, well, if you know where you weren't, if you know where you were, and now you know where you are. You do this in all three dimensions. But later on, we started doing that for airplanes. So when the pilot takes off, he puts in his inertial navigation system, and that helps make sure that they are where they need to go, even if they lose satellite signal or something. And also, interestingly enough, it is used for drill bits. Not like the little ones you put on your home cordless drill, but for the giant oil wells. because they're not just going down anymore. Nowadays, they steer those things and they go all different directions in order to access the oil. And well, you got to know where your drill bit is, and it's underground. You can't really see it. So they use inertial guidance for their drill bits, which I always thought was absolutely fascinating. But the idea here is we're using the acceleration, which is something that's relatively easy to measure, and by a ball on a spring. The more it wiggles the spring, the more you accelerate it, because keep in mind, if I've got a ball on a spring in a box, if I push the box, then the box will accelerate. That's going to accelerate the end of the spring, so it's going to push the spring, and then that will push the ball. And so if I measure how much the spring wiggles, I know how much I accelerated the box. Okay, so if I track that, I can then reverse back, doing an integration, my velocity, and then my position from that. Do that in 3 dimensions, bada boom, bada bang, you know where you're at. Okay, now let's talk a couple of interesting areas. Quite often I will do some kind of example, and this is derived from the physicist's kind of stock mathematical problem of a spherical cow in space. The cows aren't spheres, and they're usually not in outer space. But if you're thinking about a physical problem, it's nice to narrow things down, get rid of some of the complicating features, such as elaborate shapes or air resistance. Turns out air resistance is one of those things that's a little bit harder to calculate than one would think it would be. And as such, it's not great if you ignore it, but if you kind of ballpark it first, ignoring air resistance, then you kind of factor it back in, it sometimes helps out a lot. So physicists will commonly joke and say, we're dealing with a spherical cow in space. This is where I need to make a quick point. If something is in space, or it's on the moon, etc., it doesn't have air, because there's basically no air in space. There are a couple of stray oxygen atoms in low Earth orbit, don't get me wrong. But there is very much gravity. So gravity is very much still a thing in space. In one of the later videos, I'm going to dive into space travel and gravity, but I do want to emphasize here real quick, there's this common misconception that there's no gravity in space. There is gravity in space. It gets a little bit less as you get farther and farther away from something, but it's still very much there. But where we get to is this idea of free fall. And once again, in the video on space travel and orbits, etc., I'm going to dive in more so, but that's actually not for a little while, because I usually cram that in with the astronomy videos, because space. That said, if something is falling and it doesn't have something pushing back against it, you're in a rather interesting position. So if you're up in outer space and you're falling towards the Earth, you've got no air, so you have no air resistance. So gravity is just going to keep accelerating you down faster and faster and faster and faster. But it doesn't feel like the gravity is there. You feel weightless, because if you're in your spacecraft, even though gravity is pulling you faster and faster and faster towards the Earth, the spacecraft isn't pushing against you. When you're in free fall, you feel weightless. It's not that you don't have weight. It's not that you don't have gravity. It's that you don't have the normal force pushing back on you. The weight that we feel isn't the gravity pulling us down, but it's the floor pushing us up, preventing us from falling through into the center of the Earth. So if something is in free fall, without air resistance, it's just going to keep going faster and faster and faster until it goes kasplat. Now, if you do have air resistance is a rather interesting one. It's depending on your shape and the density of the air and a few other factors, but it's heavily dependent on your speed. The faster you go, the more air resistance you get. At a certain point, the air resistance is going to cancel out the force of gravity. This is why insects can drop from great heights. They have very little mass, and as such, at the point where they're fast enough that the air resistance cancels out gravity, well, they're not actually falling that fast, and so they'll just bounce when they hit the bottom. Cats from a particularly high height can actually gain a similar advantage. They splay themselves out to slow themselves down, improve their air resistance, get more of it. People, however, not the case. We can fall faster and faster and reach what we call terminal velocities, as fast as you can, because air resistance is pushing you back, and that's more than enough to make you go splat. So do use fall protection if you need fall protection, because the air is not going to stop you. I do apologize. Of course, we can see this with, say, feathers and bowling balls. Feathers have lots of surface area, very little mass, tons of air resistance, not all that much mass, so the acceleration of gravity means that, well, they don't have that much force from the gravity pulling them down, so they flutter to the surface. Bowling balls, quite the opposite. Fairly decent aerodynamic shape, not perfect, but sphere is not bad. So air resistance is relatively low, they've got a lot of mass, they're famously heavy, and so a lot of force of gravity. So they're gonna have to be going really fast in order for the air resistance to cancel out their free fall. But if there was no air, well, there's no air resistance. If there's no air, they will fall at the same rate. This is one that was shown with various experiments in the Renaissance, and then in the early 1970s, I believe this was in 1970, 1971, one of the moon landings did do an example of this. There was no air on the moon, and so drop a hammer. I don't remember what the other thing he dropped was, but a light thing and a heavy thing, they fall at the same speed if there's no air. But here on Earth, there's like lots of air, which is good because we could breathe. Now, while we're on the topic of air, let's talk wings. Okay, that fuzzy thing in the background, which is not my best choice for background pictures, is an airfoil. I'll probably try and pop it up over here. When it comes to wings, there is a lot of misconceptions because in this case, we are dealing very much with the flow of air and engaging what's known as fluid mechanics. Fluid mechanics is the study of how fluids flow, and it is famously complicated. I know a tiny, tiny amount, not a much. I've got a cousin who's pretty good at it. She got her PhD in engineering. We're all proud of her. You know how it goes. But I want to dive in just very, very briefly into wings because this picture is wrong. This is kind of what you see in a lot of textbooks. The explanation to how a wing works ends up involving forces and pressure and, yeah, this one's not quite right. It's one of those where it's got a good start and then goes off the deep end with one assumption. Okay, so the narrative here, the typical narrative you're going to find in a textbook is that as the wing flows, the air goes faster over the top than on the bottom, which causes a higher pressure on the bottom and a lower pressure on the top, and that sucks the plane up into the sky. And of course, the reason it flies longer over the top than the bottom is because it's a longer distance and the air has to get from one end of the wing to the other in the same time. This is known as the equal time fallacy, and from that statement, you know what's wrong with this. The speed and pressure, that's legit. That's Bernoulli's principle, that's real. What's not real is that the air actually has to get from one end to the other in the same time. In fact, it generally doesn't. The top one will often get to the back end of the wing faster than the bottom one does, which does mean that will cause all kinds of spirally vortices at the end of this. So a better explanation of how a wing works involves Newtonian physics, because F equals ma. Okay, so over here, one, there's a couple of things missing. Generally speaking, you'll notice that wing is angled. That's the angle of attack, and generally speaking, most wings are angled. That's a really, really big deal. Now, they are curved. They get that kind of squiggly comma shape to them quite often. They don't have to. Keep in mind, a paper airplane does not have a curve to its wing. That squiggly comma shape is what's known as camber. The more pronounced it is, the more camber it has. If it's nice and symmetrical, then it would have no camber. That kind of weird elongated teardrop shape is more or less just to make the air flow nice and smoothly so you don't have as many of the weird spirally vortexes that just create problems most of the time. Not always. Occasionally they're useful, but most of the time they're more of a pain. Okay, so what you'll notice on this one, unlike the previous one, so if I pull up the previous one, the air is going in straight, the air is leaving straight. I haven't accelerated the air up or down. In order to have a force, you must accelerate something. You must push on something. It doesn't actually have to move. It doesn't actually have to accelerate, but you got to push on something. And if it's air, it's going to move. That's not moving. So there can't be an upwards force. I don't care what you're saying about pressure, because the air isn't moving. So let's move this back. Notice how in this picture, the air is going down and back. It's definitely going back. Once again, the plane is moving through the air, or the blade's moving through the air. So it's going mostly front to back, but it's going down. We have accelerated the air down. We've exerted a force on the air. The air is being accelerated down, and thus there's an exertion of force on the plane. That is now counteracting gravity. So we are trying to counteract gravity by pushing on the air. That means the air has to go down. If you actually look at the air pressure under an airplane, you have this area right under the airplane where there is a slight increase in air pressure, not by much. Now, I did mention pressure. Bernoulli's principle, totally legit. It is definitely a thing. And we get it a little bit backwards. Think of why the air is going to increase in pressure under the wing. That's the way the wing is shoving the air down. So if I swipe up to this image, as the wing pushes the air down, that's going to increase the pressure, which is going to slow down the airflow. Once again, on the other side of the wing, that's where there's kind of a gap. The air that would be there has been shoved out of the way by the wing, so it's going to be low pressure above the wing. Pressure is force over an area. The higher pressure, the more force it's going to exert. So the bottom of the wing is going to exert more pressure on the wing. Once again, the wing is shoving it down, so it's going to push back. The air is going to go faster over the wing because now the pressure has dropped because that's the air that wasn't allowed to get back there. Now, the fact that the air is moving faster and slower is then going to enhance the pressure difference, which is going to give you a bit more force. So Bernoulli's principle, totally correct, totally applies to wings, but it's a lot more complicated than just making it run the long route. You're going to have the fact that you're shoving air out of the way. Now, side note, even if the angle of attack is 0, if you do have camber, you can still get lift because you still direct air downwards towards the ground. The air will flow across the surface. I also should point out, this has been an incredibly oversimplified description of how wings work. These things get complicated. Anything with fluids is going to get incredibly complicated. Okay, so let's change a bit of a frame of reference. So far, we have been talking about force in a nice linear fashion. If you've got one force, you got another force, they're lining up nice and neat, and they're pushing against each other, or they're adding to each other. What happens if they don't line up? Well, now we get to an area we call torque. Torque is a twisting force. So far we've been thinking about force as nice straight lines. Now we're going to think of it as spirals. We're going to have a twisting force. The units for this is going to be newtons meters. Meters as in the distance the two forces don't align. I probably should not hold my hand like that right in the light. The distance the two forces don't align. There, I'm not blocking my face from the light. We can see this on a fairly easy basis. So hold something like the handbook. If I'm holding it close to my body, I'm pushing up, gravity is pushing down. We can actually think about gravity as pulling every single atom of this book down, but that's a lot of gravity pulling, it's a lot of vectors. So we will simplify it and average where all the mass is, and we'll say it's in the center of mass, basically the average location for all those vectors. Well, if I've got it, and its center of mass is pretty close to the area in which I'm pushing pretty much straight up. I got a nice linear one. But if I put it out a bit, well, now I'm having to do a bit of a twist because this is what's providing the force, but the center of mass of my book is out over here. If I keep going further and further, once again, my shoulder is what's providing the force. It's not pushing up, it's twisting up, it's pulling this at an angle, and well, this is going to get heavy pretty quick, even though it's not heavy, because I'm having to do a twisting force, and it's getting fairly far away. The Newton part isn't particularly large. The distance part, it's getting a little bit on the long side. So this is an idea of torque. This is going to be a big deal when we jump into the wonderful world of simple machines. Levers, wheels and axles, they're all foundationally built around torque. Now, we got ourselves some torque. We got ourselves a twisting force. In fact, everything we deal with has a twisting or a spinning analog to the linear analog. Now, one of the topics I haven't dealt with is that of momentum. Momentum is a coupling of your mass and your velocity. So the faster you're going or the heavier you are, the more momentum you have, meaning it is the harder to stop you. So if you get a lot of momentum, it's going to take a lot of effort to stop you. You have a lot of acceleration to do, so you're going to need a lot of force or a lot of time to slow you down. Now, there's a couple interesting properties of this. Momentum is what we call conserved. Remember, for every action, there's an opposite and equal reaction. So if I push on you, you push on me. If in isolation, so it's just the two of us and we're floating in space, and I push on you, well, whatever momentum I had and whatever momentum you had, they're going to stay the same. We may exchange our momentums. So I may give you some of my momentum, or you may give me some of yours. But because you are pushing on me and I'm pushing on you, we can change the momentum of each other. But turns out, together, our combined momentum will always stay the same. If you play pool, this is actually kind of a big deal. Billiards, you know, where you got the balls and the stick and you hit them in the pockets. Because when you hit the balls, they're all the same size. At least they're supposed to be. So when one hits the other one, if you hit them square on, then the cue ball, the one that hit it, stops moving. And the one that you hit starts moving. And all the momentum from the cue ball is transferred, hopefully, into the ball you hit. Or maybe not, hopefully, depending on the shot you're trying to make. If you hit at an angle, you won't transfer all the momentum, but you'll notice one ball will go one way, one ball will go the other way, but if you were to average the two balls, they're still going straight on average. Now, likewise, as momentum is conserved, there is a twisting version called angular momentum. So remember, torque as angular force, and it's proportional to how heavy or how much force the thing is exerting. So this could be the force of gravity, and how far away it is. Well, if I think about that center of mass, if I'm spinning, I've got momentum. I've got a twisting motion, I've got a spinning velocity, an angular velocity, how fast I'm spinning, but also I have mass. But here is an interesting case. That may not be all in the center. My mass will be spread out. And if the mass is fairly far out, well, I've got a lot of mass moving. And so it's moving pretty quick. It's far out, and the farther out on a circle you are, the faster you spin. So what would happen if I move that mass inwards? Well, anything angular, I care about both how much I have and how far away is it from the center of rotation, from where I'm spinning. So as I move the mass in, it's going to be losing momentum because it's getting closer, except for it can't lose momentum. Momentum is conserved. It either must accelerate something else, or it's going to have to gain momentum from someplace else other than its location. That means it's going to have to spin faster. Because the momentum is conserved, I can't lose it, so I can only exchange it. As I pull the mass in, then it's going to spin faster. If I put the mass further out, I can't get momentum from nowhere. If something else won't accelerate me, then I'm going to have to spin slower because the mass is further out. Okay, so this has been a long, not overly elegant video on the wonderful world of Newtonian physics. I do recommend checking out a couple other sources. You know, always nice to peruse the internet on topics. I hope this has been of some help for you all. The next video, we'll be jumping into the wonderful world of simple machines, and then we will move on to things such as electricity and heat and whatnot in the wonderful world of physics. Things that I'm a little bit stronger on than good old motion. But until then, have a wonderful day.